Welcome students to the sixth and last lecture on determinants. As I said earlier, in this lecture I shall talk about solution of systems of linear equations. You know that an equation is said to be linear if the underlying variables have exponent 1. For example, x plus by is equal to c, or say 2x plus 3y is equal to 5. The underlying variables here are x and y, and since all of them have exponent is equal to 1, these are linear equations. When we talk about systems of linear equations, we consider multiple equations with multiple variables and we like to solve for the variables such that the obtained values satisfy all the equations simultaneously. In this class, we shall deal with either two equations with two variables or three equations with three variables. Now, consider an equation, a system of equations such as 2x plus 3y is equal to 5 and say x plus 2y is equal to 3. We know that by x is equal to 1 and y is equal to 1 satisfy both the equations simultaneously. Is it the case all the time? No. Example, consider two x plus 3y is equal to 5 and 4x plus 6y is equal to 15. Suppose you are given two such equations, it is very clear there cannot exist any x and y which satisfy both of them simultaneously, because if I multiply the left hand side of this equation 1 with 2, we get 4x plus 6y, but on the right hand side we get 15, therefore, it cannot be satisfied. On the other hand, if we consider 2x plus 3y is equal to 5 and 4x plus 6y is equal to 10, then we face a different problem. Since multiplying this equation by 2, we get the second equation, we can get multiple solutions for the above system of equations. For example, x is equal to 1, y is equal to 1, therefore, 2x plus 3y is equal to 5, 4x plus 6y is equal to 10, both are satisfied. X is equal to minus 5, y is equal to 5, therefore, 2x plus 3y is equal to minus 10 plus 15 is equal to 5, 4x 4 into minus 5 plus 3 into plus 5 is equal to minus 20 plus 30 is equal to 10. X is equal to 2, y is equal to 1 by 3, therefore, 2x plus 3y is equal to 4 plus 1 is equal to 5, and 4 into 2 plus 6 into 1 by 3 is equal to 8 plus 2 is equal to 10. Therefore, we see that we can find 1, 2, 3. In fact, we can compute infinitely many solutions for such a system of equation. Therefore, given a system of equations, we can have three possible situations. Either we can have one solution, or we can have multiple solution, or we can have no solution. Question is, how do we judge what is the situation for a given system of linear equations? So, we apply matrix and matrix inverse based techniques as follows. Let the systems of equations be A11 times x1 plus A12 times x2 plus A1n times xn is equal to B1. A21 times x1 plus A22 times x2 plus A2n times xn is equal to B2, and like that An1 times x1 plus An2 times x2 plus An times xn is equal to Bn. Or in other words, we are looking at n equations in n unknowns, namely x1, x2, xn. Note that we can represent such a system of equations in a matrix form. Ax is equal to B, where A is n cross n, x is a vector of or a one dimensional matrix of n rows and one column of variables, and B is the right hand side, again n rows and one column, or A11 up to A1n, A21 up to 2n, An1 up to Ann times x1, x2, xn is equal to B1, B2 up to Bn. Thus, very neatly we can represent the entire system of linear equations in a matrix form. Case 1. Suppose A is non-singular, then what will happen? We know that we can compute A inverse. This we have seen in our last class. Therefore, by pre-multiplying A inverse into Ax is equal to A inverse B, or x is equal to A inverse B. Thus, if A is non-singular, we get unique solution for the system of linear equations. Example, consider 2x plus 3y is equal to 8, 3x minus y is equal to 1. Therefore, in matrix notations, two, 3, 3 minus 1 multiplied by x y is equal to 8 1. Now, determinant of A, which is this matrix, is equal to determinant of 2, 3, 3 minus 1 is equal to minus 2 minus 9 is equal to minus 11, not equal to 0. Therefore, A inverse exists. How to compute A inverse? We know A inverse is equal to adjoint of A divided by determinant of A. Now, the matrix is 2, 3, 3 minus 1. Therefore, adjoint of A is equal to, we know that we change the two diagonal elements and change the sign of the two off diagonal elements. Therefore, A inverse is equal to minus 1 minus 3 minus 3 2 upon minus 11 is equal to 1 by 11, 3 by 11, 3 by 11 and minus 2 by 11. Therefore, A inverse B is equal to 1 by 11, 3 by 11, 3 by 11 into minus 2 by 11 into the right hand side of the B vector, that is 8 1 is equal to 8 by 11 plus 3 by 11 and 24 by 11 minus 2 by 11 is equal to 1 2. Thus, we get a unique solution for the system of equations. Let me now solve another problem. Suppose it is given that the cost of 4 kg of onion, 3 kg of wheat and 2 kg of rice is rupees 60. The cost of 2 kg of onion, 4 kg of wheat and 6 kg of rice is rupees 90, and the cost of 6 kg of onion, 2 kg of wheat and 3 kg of rice is rupees 70. Find the individual costs. So, we represent the system of equations as 432, 246, 623 multiplied by x, y, z is equal to 60, 90, 70, where x is price of per kg of onion, y is price of per kg of wheat, and z is price of per kg of rice. We need to find out the values of x, y, z such that all the three equations are satisfied. Therefore, we need to compute A inverse, which is we already know is equal to adjoint of A divided by determinant of A. So, we compute adjoint of A11 is equal to 4 into 3 minus 6 into 2 is equal to 0. A12 is equal to minus 1 into 2 into 3 minus 6 into 6 is equal to 30. A13 is equal to 2 into 2 minus 6 into 4 is equal to minus 20. A21 is equal to minus 1 into 3 into 3 minus 2 into 2 is equal to minus 5. A22 is equal to 4 into 3 minus 6 into 2 is equal to 0. A23 is equal to minus 1 into 4 into 2 minus 6 into 3 is equal to plus 10. A31 is equal to 3 into 6 minus 4 into 2 is equal to plus 10. A32 is equal to minus 1 into 4 into 6 minus 2 into 2 is equal to minus 20, and A33 is equal to 4 into 4 minus 3 into 2 is equal to plus 10. So, once we obtain the cofactors, we can write adjoint of A is equal to 0, minus 5, 10, 30, 0, minus 20, minus 20, 10, 10. Therefore, to compute A inverse, we need to find determinant of A. Now, determinant of A is equal to, if we expand along the first row, we multiply by the term with their cofactors. Therefore, what we get is 4 into 0 plus 3 into 30 plus 2 into minus 20 is equal to 0 plus 90 minus 40 is equal to 50, which is non-zero. Therefore, division by 50 makes sense. Therefore, A inverse is equal to 0, minus 5, 10, 30, 0, minus 20, minus 20, 10, 10 divided by 50 is equal to 0, minus 1 by 10, 1 by 5, 3 by 5, 0, minus 2 by 5, minus 2 by 5, 1 by 5 and 1 by 5. Therefore, the solution of the equations we can get by multiplying this A inverse with the B vector, which is given to us as 60, 90 and 70. Therefore, x, y, z is equal to the product of this with this, and that comes out to be 0, minus 9 plus 14 is equal to 5, 36 minus 28 is equal to 8, minus 24 plus 18 is equal to minus 6 plus 14 is equal to 8. Therefore, price of onion is equal to rupees 5, price of wheat is equal to rupees 8 and price of rice is equal to rupees 8 per kg. Let me solve another problem. The sum of three numbers is 6. If we multiply the third number and add to the first, then we get 7, and if we add the second and third number and add that to 3 times the first number, then we get 12. Find the 3 numbers. So, the above description gives us 3 equations. The first one is x plus y plus z is equal to 6, x plus 2z is equal to 7, 3x plus y plus z is equal to 12, or 1, 1, 1, 1, 0, 2, 3, 1, 1 multiplied by x, y, z is equal to 6, 7 and 12. Therefore, as before, we first check what is the determinant of A. One into 0 minus 2 minus 1 into 1 minus 6 plus 1 into 1 minus 0 is equal to minus 2 plus 5 plus 1 is equal to 4, not equal to 0. Therefore, we can compute A inverse is equal to adjoint of A divided by determinant of A. Therefore, as before, we compute the cofactors. Please check that we get the following: A 1 1 is equal to minus 2, A 1 2 is equal to 5, A 1 3 is equal to 1, A 2 1 is equal to 0, A 2 2 is equal to minus 2, and A 2 3 is equal to plus 2, A 3 1 is equal to 2, A 3 2 is equal to minus 1, and A 3 3 is equal to minus 1 again. Therefore, writing it in a matrix form, we will get adjoint of A is equal to minus 2, 5, 1, 0, minus 2, 2, 2, minus 1, minus 1. Therefore, A inverse is equal to this divided by 4 is equal to minus 2, 0, 2, 5 minus 2 minus 1, 1, 2 minus 1. Therefore, the solution of the equations is equal to A inverse B is equal to 1 by 4 into minus 2, 0, 2, 5 minus 2 minus 1, 1, 2 minus 1 multiplied by 6, 7, 12 is equal to 1 by 4 into minus 12 plus 24, 30 minus 14 minus 12, 6 plus 14 minus 12 is equal to 1 by 4 into 12, 4, 8 is equal to 3, 1, 2. Therefore, the three numbers are 3, 1 and 2. I suggest that you put these values in the equations and you see that all the three equations are satisfied by these three values. Another way of solving is what is called Cramer rule. Here we won't explicitly compute the inverse, rather we shall solve the system of equations by computing different determinants, and with the help of that we shall compute the values. The idea is, if the given system of equations are A x is equal to b, where A is n cross n, x is n cross 1, b is n cross 1, such that A is non-singular and b not equal to 0 vector, that is a n cross 1 matrix where all values are zeros. So, if B is not a 0 vector and A is non-singular, then the three solutions, then the solutions of the three equations can be computed as follows. Let me illustrate with 3 by 3. So, let D is equal to determinant of A. Let D1 be the matrix obtained by replacing the first column of A with B vector. That is, D1 is equal to determinant of B1, B2, B3, A12, A13, A22, A23, A32, A33. Similarly, let D2 be determinant of the matrix A11, B1, A13, A21, B2, A23, A31, B3, A33. That is, we have replaced the second column of a matrix by the B vector, and similarly compute D3 as determinant of A11, A12, B1, A21, A22, B2, A31, A32, B3. Then x is equal to d1 upon d, y is equal to d2 upon d, and z is equal to d3 upon d. I am not proving it, but I am verifying it with the same example which we did just now. So, verification: A is equal to 1 1 1, 1 0 2, 3 1 1 into x y z is equal to 6 7 12. We knew the answer is 3 1 2. So, we solve it using Cramer's rule. We know D is equal to determinant of A is equal to 4. D1 is equal to determinant of 6 1 1, 7 0 2, 12 1 1 is equal to 6 into 0 minus 2 minus 1 into 7 minus 24 plus 1 into 7 is equal to minus 12 minus 7 plus 24 plus 7 is equal to 12. Therefore, the value of the first variable is equal to 12 upon 4 is equal to 3. Now, D2 is equal to determinant of 1 6 1 1 7 2 3 12 1, and this we get by replacing the second column with the B vector 6 7 and 12. Therefore, its determinant 1 into 7 minus 24 minus 6 into 1 minus 6 plus 1 into 12 minus 21 is equal to minus 17 plus 30 minus 9 is equal to 4 Therefore, value of y is equal to 4 by 4 is equal to 1. In a similar way, D3 is equal to determinant of 1, 1, 6, 1, 0, 7, 3, 1, 12. We have replaced the third column with the v vector is equal to 1 into 0 minus 7 minus 1 into 12 minus 21 plus 6 into 1 minus 0 is equal to minus 7 plus 9 plus 6 is equal to 8. Therefore, z is equal to 8 by 4 is equal to 2. Therefore, we see that using the Cramer's rule, where we did not explicitly compute the A inverse, we could solve the systems of equations. All the problems that we solved have the A matrix is non-singular and therefore, determinant of A is non-zero. Question is, if A is singular, then what happens? So, determinant of A is 0. Therefore, we need to do the following. A, if determinant of A is equal to 0 and adjoint of A multiplied by B is equal to 0, then we will have multiple solutions for the system of equations. And B, if determinant of A is 0 and adjoint of A multiplied by B is not equal to 0, then there will be no solutions. Illustration: consider 2x plus 3y is equal to 5 and 4x plus 6y is equal to 10. Now, A is equal to 2, 3, 4, 6. Therefore, determinant of A is equal to 0. Therefore, we compute adjoint of A into B is equal to, we know that for 2 cross 2 matrices, to compute the adjoint, we interchange the diagonal elements and we change the sign of the off diagonal elements. Therefore, the adjoint of this matrix is 6, minus 3, minus 4, 2, and if we multiply this with 5, 10, we get 30 minus 30 minus 20 plus 20 is equal to 0 0 is equal to 0. Therefore, determinant of A is 0 and we find adjoint of A multiplied by B is 0. Therefore, as we have seen, there are infinitely many solutions. But suppose we have new example, 2x plus 3y is equal to 5 and 4x plus 6y is equal to 15. Therefore, determinant of A is equal to 0 and adjoint of A into the B vector is equal to 6 minus 3 minus 4 2 multiplied by 5 and 15 is equal to 30 minus 45 and minus 20 plus 30 is equal to minus 15 10. This is not a 0 vector. Not a 0 matrix of size 2 cross 1. Therefore, as we have seen that determinant of A is 0, but adjoint of A multiplied by B is non-zero. Therefore, there is no solution to this system of equation, or this given system of equation is inconsistent. Okay, students, with that I conclude my series of lectures on determinants. I hope that you will find the lectures and the examples that I have done useful in solving many other problems. Thank you so much.